So welcome everyone to the second session of HELG. So our first talk today, the first talk of this session will be by Vincent Cohen-Addad. So first, I should tell the audience that the audience cannot unmute themselves of their own accord. So if you have a question, please type the question in the chat box, and I will read it out loud and make sure that Vincent gets a chance to answer it. Good. So as I said, the first talk is by Vincent. He will tell us about some exciting recent advances in clustering in various settings.
Thanks a lot, Michael, for the introduction, and thanks a lot for the invitation. I'm very happy to be talking today. So indeed, this is a series of work that I've been working on to try to understand the complexity of metric clustering. So this has been a series of work done with a lot of people that I'm very thankful to, and it's a collaborative work. And today the topic of the talk is metric clustering. So not to be confused with graph clustering. Metric clustering, you are given a set of points in a metric space. So you can see weights between points, and this weight satisfies the triangle inequality. And so there are distances between points. And we think of points that are close to each other. In a clustering, we would like to find a partitioning such that points that are close to each other should be in the same path. So this has like a different motivation. One motivation for which we had also some practical results recently is for partitioning real-world networks or road networks coming from maps. So for example, you can try to compute a clustering of a set of points in that like come from road network representing like houses close to each other, if you are interested in, for example, in redistricting or facility location. But clustering is also used to in machine learning to identify patterns in data. So for example, if you set your distances in such a way that images that represent ducks are close to each other, and images that represent animals with long ears are close to each other, then if you apply a clustering algorithm, then you will get two groups. You want to get two groups such that ducks are in one group because they are close to each other, and animals with long ears are close to in another group because they are close to each other. Okay, so these are like classic use of clustering, and so these are the main motivation for looking at the problem. And we want to define the problem as follows, where you are given a metric space. So it's really like a set of points and a distance function on this set of points. And you have what we call as input, we have a client set, which is a set of points in the metric space, and a set of candidate centers, which is also another set of points in the metric space, together with a parameter k. And your goal is to find a set of k representatives that we'll call center or facilities, and such that you minimize, they have to be picked from the candidate center set, and you have to minimize the sum of the over all clients of the minimum cost to the closest representative. And in the k-median problem, the cost is given by the distance, and the k-means problem, the cost is given by the square distance. And there are some settings for which k-means is actually somewhat easier to deal with, in particular for like practical algorithms. Okay, so that's the k clustering problem that we're going to look at, like with k-median, k-means being like the two flavor of it. And when we consider this problem, it's also interesting to look at a soft version of the problem. So this version of the problem with a soft constraint, which is kind of a Lagrangian relaxation of the problem, where the input changes. So now instead of a parameter k, I'm going to give you a cost function over the candidate centers. And now I'm not forcing you to pick at most k representative, at most k centers. You can pick as many as you want, but now you have to pay a cost for opening the centers depending on this cost function that they give. Okay, so the more centers you're going to pick, the higher the price, but on the other hand, this cost for serving the client, for as paying the cost for the clients, is going to be small. So there is kind of a trade-off. So it's a way to relax the constraint on k. So it's also useful to get to keep this definition in mind. Okay, so today I'm going to try to bring you through a journey through clustering, in the sense that I want to consider these problems in different metrics. So when the metric that I defined satisfies some bias constraints. So of course, if you just satisfy the triangle inequality, you are in a general metric realm, and we know that it's kind of hard. We're going to try to discuss that. But now you can relax it, right? So you can be in Euclidean space, but high dimensional. You can be in metrics that are defined by a shorter space metric over a planar graph. You can be in low dimensional metric. And when I was designing this slide, actually, I realized that the talks are has actually two parts. So the first part is like the standard part where we're gonna say, okay, there is this clustering objective, and now I'm gonna try to get the best possible bound for, I don't know, planar or low dimensional. And so we learn on the clustering objective, we learn how easy it is in different metrics. But there is the second part of the talk where, in fact, I want to convince you that clustering is such a fundamental problem that it can make us understand new properties or differences between very fundamental metrics. For example, the L1 metric, the L2 metric. I want to use clustering as a tool to understand more about the metrics. So not only metrics that help us design good algorithms, metrics that help us design good algorithms for clustering, but also clustering as a tool to understand metrics. Okay, so to understand these two parts, I want to explain very briefly how you can see clustering as a very fundamental problem, as a set cover problem on the metric space. So if you gave me an instance of set cover with a universe U and a set system S, some subsets of U, and you ask me whether there exists a solution of size at most k. So namely a collection of k sets from S that covers the whole universe. This is the standard set cover problem. And now I can transform it into a k-median instance as follows. So for each client, for each element of the universe, I'm going to create a client. For each set, I'm going to create a candidate center. And I'm going to set the distance between the client and the candidate center to be 1 if the client belongs to the set. And otherwise, I'm going to set it to a very large number. Okay. Now the goal is to decide whether there is a solution of total cost at most to the size of the universe. Because in that case, I know that every client is paying 1, which means that I can pick k candidate centers so that everyone belongs to at least one of them, to the corresponding set. Okay. So in that sense, k-median is a metric set cover. So let me make it slightly more formal. So we're going to work with the max coverage problem, where you have an input, you have a universe and a collection of subsets, and a parameter k. And you want to cover a maximum fraction of the universe by picking at most k sets. Okay. So there is this theorem, separated theorem by Feiger from the 90s, which tells you that it's going to be NP-hard to distinguish between a yes instance where you can cover everyone. Okay, you can pick k set and cover the whole universe, or you can, no matter which sets you pick, if you pick only k of them, you can cover at most 1 minus 1 over refraction. So if we go to the k-median instance, what we can do is that for each element of the universe, I'm going to create a client, and for each set, I'm going to create a candidate center. And I'm going to put a distance 1 if between the candidate center that corresponds to set S, if the clients that the universe that correspond to this client is in S. Okay, so if the element belongs to the set, it's 1. If it doesn't, it's 3. Okay. So now what do we get? So in the yes case, when there exists k candidates, there exist k sets that cover the whole universe, then it means that there exist k candidates that cover that, such that each client is at distance 1 of at least one center. So the optimal k-median cost is at most U. In fact, it's exactly U. In the no case, then no matter which k subset of the candidate center you pick, you are going to cover at most 1 minus 1 over refraction of the client. So for this 1 minus 1 over fraction of the client, they're going to be paying 1, but the rest must be paying 3. Okay, so in that case, you're going to, what's your total k-median cost? It's at least 1 minus 1 over e times 1 plus 1 over e times 3, which is what you pay if you are not covered. covered. Okay, so in that case, you know that the K-median cost is 1 plus 2 over E. So the result by Feiger tells us that, you know, and it's a result by Guo and Kula that tells us that, you know, if it's going to be hard to approximate the K-median problem, for example, within a 1 plus 2 over E minus epsilon fraction factor. Okay, so that's how you can see the K-median problem as a set cover. But now let's step back and ask what does the reduction require? So one property is that if a universe element belongs to a set, then the distance between the two corresponding points is 1. Okay, and otherwise it must be 3. And this 3 that I set up here, you know, I would like to set infinity because then I will get a higher gap. But you know, I can't because, for example, in this setting, if I have you know U1 and U2, U1 belong to S, so I put 1. U2 does not belong to S, so I would put a very large number. But you know, maybe there is another set for which U1 and U2 belong, to which U1 and U2 belong. And in this case, you know, this guy is at distance 1 from here, so at distance 2 from U2, and so at distance 3 from S. So if I want to satisfy the triangle inequality, I can put a number that is at most 3 on that distance here. Okay, so the triangle inequality tells us that, you know, okay, it's 1 and 3, so 1 plus 2 over E is the best you can get through this reduction. Okay, but now one can ask the following question. If we have more constraints on the metric, in the sense that, you know, now it's Euclidean, I need to embed this. These points need to live in a Euclidean space. What if it's a Euclidean space of low dimension? What if it's a Euclidean space of high dimension? What if this graph, these distances should come from the shortest path metric of a minor free graph? What if it's the distance between elements is given by some Jakob distance, by some edit distance if these elements are strings? So now we can ask, how does the harness is going to change if I have more and more constraints? Okay, and that's what I want to investigate some of these directions during the rest of the talk. So the first part is going to be looking at, you know, planar graphs. So in the sense that I'm going to look at shortest path metric of the planar graph. And the other, and also like it's very similar so to low dimensional Euclidean space. And in the second part of the talk, I want to look at high dimensional Euclidean space and see what kind of structure this imposes, right? Because that's also a complement to the first one. Okay, so let me dive into first the first is and second bullet. So what we knew about K-median in low dimensional Euclidean space was that you could get a 1 plus epsilon approximation for the K-median problem. And this dates back from the 90s with the first work by Raghavan and Rao, which gave like quasi-polynomial running time, you know, for d greater than 2, the number of dimensions being greater than 2, which was then improved in 99 to 2 to the 1 over epsilon and d, some function of 1 over epsilon and d, and then near linear time. And out of these two works, there were two questions. So what about K-means? Because as we will see, for K-median, it works very well. For K-means, it's a different story. And what about slightly more general metrics? So if you again, take this perspective on learning about metrics, you know, these results hold in Euclidean space. And now if we go to doubling metrics, and a doubling metrics is simply a slight generalization of Euclidean space. The only thing we're going to assume it's any metric, any discrete metric, but with the additional constraints that any ball of size of radius 1 can be covered by a constant number of balls of radius 1/2. Okay, and this for all scales. And so if we just take out this property from the Euclidean metric, this constraint out of the Euclidean metric of low dimension, can we still recover these results? So these were two open questions out of this work from the 90s. And to understand the limitation of this work, it's good to look at the approach that they were using. So they were using this classic approach of not classic at that time, so this breakthrough approach of quadtree dissection, which take your set of points in, like, let's say R2 for now to make things simple, and then take a random recursive decomposition. So, you know, you go recursively top down by doing like hyperplanes or lines here. Okay, and you have a line at the first level, and then you go recursively in the two parts that this line define, and so on and so forth. And then once you have drawn your lines, then you place p portals on the boundary of on the lines, on the boundary of the regions you have defined by drawing your lines. Okay, And then you want to restrict your attention to solutions that are structured, in the sense that if a client that lies on some region wants to connect to a facility that is in a different region, then it can do so, but it must go through a portal first. So you're going to pay a little detour. Instead of going in a straight line, you're going to go through the closest portal and traverse and cross the boundary, cross the line only at the portal. And once, if you can prove that you have a good structured solution, then there is a simple dynamic program that go bottom up on this tree, and where the table entry is given by the distance from each portal to of the region to the closest center, and then if you have this information, you have like very nice sub problems, and it's easy to go up. The only issue is that you need the running time is going to be exponential in the number of portals you're going to have, because that's how you define the sub problem, and you have like if you have p of them, then basically you can do it in 2 to the p, and then near linear time. And the question that came out of this, is a natural question: is how large should P be? Okay, because you want something that is polytime, you want something as efficient as you. So of course here, if I replace P by a constant, then you're happy, you're done, you are n poly log n, so you're very happy. If P is log n, then now you start to be in trouble. Okay, so just to see how large should P be, there is a very simple one-page analysis that I'm gonna do right now, which is very nice and simple. So if you have the facility and the client that are split by a line at length L, of length L, okay, so if the line here that splits the two clients is of length L, then because you put P portals, like on this line, the detour is going to be L divided by P. Okay. So that's some bound. Now you can ask, okay, I'm gonna try to amortize this detour. And you can ask, what's the probability that the client C and the facility F, or the center F, are separated by a line of length L? And in fact, you can choose that this is, the distance between the two divided by L. Then you can just write what's the expected detour caused by a line of length L. It's, the probability, which is here, times the detour. And these nice things cancel out. You can see that the L on both sides, they go down, they cancel out. And so you get distance between the two divided by P. And that's exactly what they pay in opt divided by P, which is the number of portals you make. So it's very good because it's proportional to what you're going to pay in opt, the optimum solution. So L, the line L that can separate C and F, can take basically theta of log n values, different values. So now if you sum up over all these values that this line L can take, because every time you divide by 2, more or less like this, when you go recursively, the total detour is going to be log n divided by P times the distance. So now, if you want a 1/epsilon approximation, you have to pick, P to be like some polylog. Okay. And now the running time becomes exponential. Okay. So there are two problems here. Is that we would like to use less than log n portal. We want to use little of log n portals, because that's how we can get an efficient running time, and that's how we could get below, quasi-poly. But we don't really know how to do it for simpler problem in doubling metrics. So this is like not super nice. And also this analysis, fails miserably when you look at k-means. Because now what's the expected detour? If I want to do the exact same thing, if I want to amortize again, what's happening? Well, the probability remains unchanged, right? You have like the distance divided by L, that's the probability to separate C and F. But of course, now what you are paying is not L divided by P and things cancels out nicely. It's L squared divided by P squared, because you're squaring the distance, okay? So now the expected thing is like L divided by P squared times the distance between the two. But this is meaningless for us, because of course this CF is like in the optimum solution you are paying this CF squared, but now L, you have no relationship between the two, not necessarily, right? L can be much longer than this CF, right? And now there is no relationship. So for example, in the left hand side in this drawing, you have a very clean example where this fails, right? So if this is your optimum solution with the green, the clusters, and the points are the clients in black. Now if you have a line like this and you make a detour, let's say the line has length n, then you'll make the detour of n divided by p squared. It's much greater than n, which is opt, for example. So this is you can show like this is never going to happen. So you can't make detours like this. If you want to show that there exists a good structured solution with less portals, you need to argue differently. Okay. So how to solve these issues? So what we showed in 2016 with Klein and Mathieu, and which was shown in another paper with Frickstadt, Rezapour, and Salavatipur, is that a local search algorithm with neighborhood size like 1 over epsilon squared or 1 over epsilon to the order d if you go to higher dimension will give you 1 plus epsilon approximation for k clustering, so k means, k median, in planar metrics or Euclidean space of low dimension or doubling metrics. And the algorithm here is
question.
Oh, yeah, sorry.
Probably question for the previous slide. I'm reading. If you are using grids, why isn't there a floor function somewhere happening on the slide?
Oh yeah, there should be a floor function somewhere. Yeah, but so it doesn't change up to constant factor. It doesn't change much the analysis in total. So, but yeah, you can do some pre-processing for avoiding this issue with grids.
Thanks.
So yeah, so going back to this algorithm, so the algorithm is really like the naive algorithm you can think of, which is that you have your set of centers, your actual solution. You try to make a change by changing 1 over epsilon squared centers, and you obtain a different solution. You ask whether the cost is better. If the cost is better, you keep it and you repeat, and you keep on improving. If the cost is not better, then you try another set of moves. And you will need to try all possible moves in the sense that you try all subset of size 1 over epsilon squared to remove and to add to your solution. Okay, so that's the naive local search algorithm, and this gives you 1 plus epsilon. And here I'm not going to dive into the analysis, but the main idea of the analysis is that in all these metrics you have the isoperimetric inequality in the sense that if you look, you can define small sphere, and such that small balls, such that the inside of the ball is of cost which is much larger than the cost for the thing on the outside, on the boundary. In the sense that if you draw a circle in the plane, the perimeter of the circle is much smaller than the area of the circle of the disk. And so this is crucial for local search, because in that case, what local search will do is that what matters is the inside of the ball. So the inside of the ball, if the ball is small enough, local search can get it right. And on the boundary, you can mess around. You can mess up a little bit on the boundary, by constant factor, by a few constant factors. But then, because what matters is really the inside of the ball, because that's where you have the more mass, you can charge, how you have separated the instance, you can charge it to the cost inside. And that's really the key here. And that's why it works for many problems and many metrics. So for example, it works for planar, it works for minor free, it works for low dimensional, for clustering. But for planar, you can also show that it works for other problems like vertex cover, dominating set. So these things work for many problems thanks to the isoperimetric inequality. Okay, but there are 2 issues, I think, with this. The first one is the running time, because I have described it. You have to try all possibilities of changing centers inside with centers of changing center of your current solution with all the possible centers that are available. So okay, so if you try this naively, it's like 1 over epsilon squared swaps, okay, or 1 over epsilon to the order d swaps. And if you do it brute force, that's n to the 1 over epsilon square, n to the 1 over epsilon to the d, which is okay, poly time. So we made some progress. Maybe it works for k-mean, so fine, but still not very satisfying. And also, interestingly, it does not work for facility location where you have different opening costs. So in fact, there is this result by Arya et al. From the 2004 that shows you that even on a star, this local optima can be as bad as factor 2. And really, this comes from the fact, it's a star, so it's a planar graph, so you can say, okay, there is still some isoperimetric inequality. But here, you can mess around the isoperimetric inequality because thanks to the weight. Because, as I said before, if the boundary is small compared to the inside, the cost on the boundary is small compared to the cost inside, then you can argue something. But now if I play with weights, I can put a lot of weight on the boundary. And now the cost of the boundary is not related to the cost of what's inside. And then you lose the isoperimetric inequality. And this is nice to see that indeed it's really the isoperimetric inequality that is making things work here. And if you have waves, then you can fool it, and then you can fool the other person.
Vincent, so for the local search, wouldn't you also need to bound the number of iterations? So somehow
That's right. That's right. That's a very good point. So for making this work, we are enforcing that at each step you make enough progress by a multiplicative factor of 1 plus epsilon or something, and actually 1 plus epsilon over k. And if you can't make progress, then you stop. But you can show that you stop at some point that is good enough. And if you right, and otherwise you converge. You know that you converge. If you start with something, okay, maybe you need to start. That's also true. You need to start with a solution that has reasonable cost, like some polynomial factor, polynomial approximation.
Makes sense.
Yeah. Thanks a lot. Okay, so how can we try to resolve these two issues? So one idea that we had was that we want to bring together local search and the old approach. That's what we want to do for low-dimensional Euclidean space. So we want to use the quadtree dissection to find the best local move. So let's look at a solution A, and the best solution A prime, such that it differs by at most 1 over epsilon centers, in the sense that A prime is the best local move out of A. That's the best way you can improve A. Okay. And then you ask, when are 1 over epsilon to the order D portals good enough? So if a client C is separated from a center F that serves it in A prime by a line whose length is proportional to its distance to F, then we are happy because we can make a worst case argument. Before I was making an expectation argument that was not working because the amortization was not working because of the square. Now, if I can make a worst case argument. I can say, okay, the distance is like this. So if I put like 1 over epsilon portals, then the detour is going to be good in the worst case. So we are happy with 1 over epsilon portals if the client C is separated from the center F by something that is reasonable. Okay. Now, the observation we made was that what is the probability, instead of looking at this amortization, which was not working, let's look at the probability that the number of putting a constant number of portals will not be good enough for client C, in the sense that C will be separated from F by a line that is much longer than the distance between them. And we can show that this is at most epsilon. And we say that in that case, the client is badly cut. Okay, so the idea in a Soda paper 2018 was that if let's look for the badly cut clients, let's do something crazy. Let's pay something which is like constant time what they pay in art, constant time what they should pay in the best local move. So we're gonna say, okay, we're gonna do something crazy. It doesn't matter. We are gonna reassign them somewhere else. It's a suboptimal move, but okay, let's do it. But okay, if we pay constant time what they're paying art, then since each client is badly cut with priority epsilon, the total cost increase for dealing with the badly cut client is only order epsilon art. So of course, I don't know exactly, but that's the main idea. It's how we can bound the reassignment cost for the client. Okay, so I've not given the detail of that. I don't have much time to give it, but that's the main idea. If the badly cut clients, there are only an epsilon fraction of them, so we can do something crazy about them. And the remaining clients, because there is this worst case bound that happens, we can just use portals, even for k-means. And so in the Soda paper, we showed that you can get the best local search move in time 2 to the 1 over epsilon to the order D and log n. And the overall running time, just because of what we just discussed, is going to take another factor k, because that's the time you take to converge. So you get you can implement the local search in a time that is like nk log n. And of course, you don't get a very good local optimum. You get something that is good enough, not an exact local optimum, but something that is close enough to a local optimum. And then more recently, we got a one-shot approach where you don't have to do these convergence steps. You can just start with a constant factor approximation, then apply this idea on top of it, and directly get a 1 plus epsilon approximation. So you can remove the k from the above running time, and we managed to get a near linear. So that's how we solve some of the issues. So for example, the running time of local search for planar graph and minor free graph still remains n to the 1 over epsilon square. So the idea I just described doesn't work for planar, and it's still an open problem to get 1 over epsilon square for planar. And for now, okay, now for low dimensional Euclidean space and doubling metrics, these also work for doubling metrics, we can get near linear time. And how did we address the facility location issue? So again, the new idea of these badly cut clients helped us also work for facility location. So that was a good news. So this worked. But for planar, again, we required a new idea. We get the first polytime approximation scheme last year with Martin and Michał Pilipczuk. And it remains, again, open to get a faster algorithm for planar. So, getting efficient algorithm for clustering in planar graph still remains an open question. Okay, so that was the first part of the talk, where we try to understand how fast can be local search, or like all the best known algorithm we have for clustering in these metrics. So in planar and minor free, we've seen low dimensional, but in doubling metrics. There's also bounded Howie dimension that Andreas Perlman and David Solpik have also worked on recently, and they got some approximation schema as well. And now I'm making progress because I managed to cluster this clustering map. So I'm starting to be happy. So, and I'm wondering whether my current clustering that you're seeing right now is a good clustering. And for now, I'm happy to say that general metrics are not easy for sure. We have seen the reduction. These metrics are easy because we can get 1 to the epsilon. And now there's the high dimensional case. So high dimensional Euclidean case, are they easy or not easy? And high dimensional is interesting because it's also something that happens a lot in practice. In the machine learning literature, they look at high dimensional Euclidean space. And, can we get something reasonable there? And here, high dimensional means different things. So you can think of high dimensional as being like points in, vector in a high dimensional Euclidean space. And this dimension can be at least log n, sometimes n, it depends. Sometimes you can go from n to log n using dimensionality reduction techniques like Johnson-Lindenstrauss, for example. Sometimes you can't if you are in the L1 distance, for example. So Johnson-Lindenstrauss only works for L2. If you are in L1, then it's unclear. So, there are all these questions. So the next part of the talk is trying to understand what's happening in the high dimensional setting. And in particular, can we try to see what's happening if we have like L2 or L1 distances? Okay, so what do we know about LP metrics? So we know already a few things. We know parameterized version. So you can see what I've discussed before on the low dimensional case as a fixed parameter analysis of clustering in Euclidean space, where the parameter is the dimension D. And what we show is that if you have parameter D plus K, so you parameterize by two things, D plus K, then you can solve it exactly in n to the dk, and this is tight based on ETH. Okay, so now we can relax. We're gonna say, okay, I'm only after 1 plus epsilon, but then I don't want to parameterize by both D and K. I can, for example, first parameterize by D, by the dimension. And that's what I talked about before. There was no dependency, exponential dependency on K. Actually, there was no dependency at all on K at the end. It was only like 2 to the 1 over epsilon to the D and n polylog. So if you get parameterized by D, then it's NP hard, but you can also get 1 plus epsilon. Now, interestingly, if you parameterize by K, so now you're back to high dimensional case. You can get 1 plus epsilon in time f of k epsilon and polylog n. So these two running time are matching. It's just you just swap the two parameters. It's pretty nice. And now if you relax and if you forbid any parameterization, then you have this very nice work by Armanian, Norozifard, Svensson, and Ward, who showed that you can get 6.357 approximation for k-means and 2.6 for k-median. And these two bounds are slightly better than what we can get in general metrics. So in fact, right, from an algorithmic perspective, it seems that we can use a little bit the L2. This is for L2 only. We can use a little bit the structure of the L2 metric to get better algorithmic bounds, approximation bounds. Okay. So what do we know in terms of lower bounds in terms of hardness of approximation? So for the general metric, we know that I have shown you the reduction. For k-means, it's a 3.94. For k-median, it's like 1 plus 2 over e, which is 1.74. And this derives from Guo and Coulomb. And then there was a sequence of works by Trevisan and also by Gautam and Indyk, who showed that it's APX hard. So you can't get an approximation scheme in high-dimensional Euclidean space unless you are, of course, parameterized by k. But the hardness of approximation was something like 1.001 or something like that. So pretty small hardness of approximation. And you know, in L1, this was requiring a lot of dimension, like n dimension, and in L infinity, this was for log n dimension. So that was pretty strong. Okay, and so what we managed to show last year with the Kartik was that for L1 metric, in fact, you can get better bounds. You can get 1.56, 1.14 for so that's for the L1, which is like you know, and we see some kind of discrepancy here. We see that L1 seems harder in the sense that the bound we managed to prove, and of course it's not really that it seems harder, it's just that we are too stupid, but it seems that the L2 bound we proved are somewhat weaker. But for L infinity high dimension, say log n dimension, because n dimension is trivial, but that's not, but log n dimension is as hard as the general metric case. So L infinity is as hard as the general metric. L1 seems somewhat hard, but much easier than the general case, and L2 seems even easier. And I'm going to try to explain a little bit how we got there, and what were the main ideas. So if you want to prove some hardness for some high-dimensional Euclidean case, one thing you can try to do is to prove hardness in the general metric case. Okay, as we did at the very beginning, we take this. We build this instance that is hard, where we only have to satisfy the triangle inequality constraint. Then we take that instance and we embed it. We embed the gadget into Rn. Okay, we try to find a mapping of each point to some vector in Rn. Okay, and then we're done. Of course, it doesn't really go like this. The third step is that you realize that you won't be able to embed such gadget without messing up the distances, and you know you're gonna try to embed it, but then you know some distances that were like 3 before are now getting much smaller. Some distances that were 1 before are gonna be much higher. So now you realize that if you mess up like this, you are gonna break the gadget, and then you have to think about some gadget that you can embed. Okay, so for example, the issue we have with the reduction I showed you before, the general metric, is that on both sides, so on the universe element side and on the candidate center side, the degree for the one edges is very high. So in the sense that one element can belong to many sets, so it has distance 1 to many sets and distance 2 to the rest. And similarly, a set has distance 1 to many elements, because a set can be of arbitrary size. So this is bad because for the bicyclic on n vertices, or n by n vertices, where you put one for between distances 1 between points that are across and distances 2 between points that are on the same side, is really hard to embed. You will suffer a lot if you try to embed this metric here. You will suffer a huge distortion. So you know the instance I've designed before for the set cover reduction is very close to this bicyclic, right? You just remove some of these edges that are 1 and you put 2 instead, but you know it's gonna be, and you put 3 instead, but it's gonna be hard to embed. So here's the fix we came up with, which is that you take a vertex coverage instance. So we start with a slightly different problem, which gives you a graph G and a parameter K as input. And then your objective is to cover a maximum fraction of the edges by using at most K vertices. Okay, so it's like a vertex cover, right? It's some rephrasing of vertex cover. And there are these two results by Ostring-Kod-Safra and Ostring and Stankovic that show that it's in unigame hard to distinguish between a vertex cover where you can cover everyone, like you can pick K vertices and cover all the edges, or a vertex cover where you can pick K vertices and cover at most a 0.9292 minus epsilon fraction. Okay. Okay. And of course, because it's a vertex cover type instance, you can also see it as a max coverage instance, as I said before, which is that think about the edges, because this is what you want to cover as your universe elements. So these are the edges that are going to be the clients, and the vertices are the sets. The vertices are the one that covers things. They cover the edges and vertices, the adjacent edges. So basically, in this reduction, we would think of edges as client and of vertices as candidate centers. And now we start to be slightly happier, right? Because the degree of the client is 2, because you have edges, and an edge can be covered by at most, actually by exactly 2 candidate centers, which are the 2 vertices that are adjacent. So now we have much more structure on the input, right? We have low degree on one side, high degree on the other, but we have some more insight. So what we showed is that for k-means, it's in L2 metric, it's going to be unique and hard to distinguish between an instance of where the total cost is n prime from an instance where the total cost is 1.15 n prime. Okay, and I'm going to try to describe the reduction. It's very simple. So if you were working again on the general metric setting, what you would do is the same thing as we discussed before. So on the one hand, you put a point for each client, which correspond to an edge. Okay, and on the other hand, you put a point for each candidate center, and these are the vertices. Okay, and now if you have edge uv1, you put distance 1 to the candidate center that corresponds to vertex u, and if it's an edge that has nothing to do with vertex u, you put a distance 3. And if we do this reduction, we know that things are looking good for us. We can have somehow we can have the maximum gap we could hope for this problem, right? We can go from 1 to 3, and we know that going higher than 1 and 3 for the distances is not going to be possible, because even in general metric space is not. So what we want is like this 1 and 3 is like the best we can do. And now, how can we try to get an embedding? How can we embed this instance onto a Euclidean space of high dimension? And the cute thing here is that there is a very natural embedding. So take number your vertices from 1 to n, and the vertex vi, you put a coordinate of 1, you put value 1 at the ith coordinate and 0 otherwise. And for an edge vi vj, you put 1 at the ith coordinate, because it's the vi, and 1 at the jth coordinate, because it's touching vj as well, it's adjacent to vj. Okay, and this is how you embed things. So we embed into n dimension the number of vertices, but with L2 we will apply Johnson-Lindell-Strauss guarantees that this also would work on log n. But that's a natural reduction. And what do we get out of it? We get that for each edge vi vj, the distance from the edge, the clients that correspond to the edge, to the candidate centers that correspond to either vi or vj, the distance is going to be 1. And that's 1 because it's exactly you can see, right, the vector that corresponds to the vertex and the vector that corresponds to the edge, they only differ on 1 coordinate, which is like between vi and edge vi vj. It only differs on our j's coordinate. So the distance is 1. Now, if you take another unrelated vertex vl, where L is different from I and J, then now it differs on 3 locations. It differs from I, from J, and from L, which is a different location. Now, what we see is that, okay, we had 1 if it's covered and 3 if it's not covered. And that starts to look good again, because it's exactly what we wanted from the original reduction, which was like, 1 if you are covered, 3 if you are uncovered. Okay. So that's the best that then we can use. We can design the best possible gap out of this problem, which is that if vertex coverage is 1, then the k-means cost here, because here I'm looking at the squared L2 distance to avoid taking the square root at the end. Then it's going to be the total number of edges. That's the number of clients. And if the vertex cover is at most 0.9292, then you get, for 0.9292 fraction, you're going to cover with 1, but for the rest, the remaining, the 1 minus 0.9292, you're going to pay 3. So that's exactly 1.15. And that's how you get a gap here. Okay, so Okay, so what did we do? So we proved some hardness in the general metric case, which was not good because now the gap is only 0.072. So instead of like 1 over e, because we were going from 1 minus 1 over e to 1, now the gap is like 0.9292 to 1. So that's a much smaller gap. But we have a way to embed that doesn't lose anything for the k-means problem at least. We get more or less a pretty good gap. And so what we did in a follow-up work with Wuyong Li is also that is trying to reconcile these two objectives, right? So because first objective is to get a hard problem in the general metric case, and the second one is to embed. And now what we want to do is make these two touch, right? We want to have a hard problem that is easy to embed. Okay. So we came up with this new problem, which goes a little backward when the first time you see it, but yeah, I'm going to try to explain to you that is very nice in the sense that it's directly embeddable. If you can get good bounds, good hardness bound for this problem, then you can embed it directly and get a very good gap in Euclidean space. The problem goes as follows: your input is a set of t tuples, where t is a parameter, but let's say of constant. So t tuples of a universe n, and you get a parameter k. And now you want to distinguish between the two following cases. So there exist k t minus 1 tuples, such that for each of your t tuple, there exists a t minus 1 tuple that is contained in it. Okay, so you know that's exactly what you want, and that's where you can cover everyone. So the covering is defined by the center being included in the point, if you think about it that way. And the soundness goes as follows. So for any set of k tuples, for any set of size k of t minus 1 tuples, you have only an alpha fraction of the t tuples that contain one of the k t minus 1 tuples. Okay, so it's almost immediate that the same embedding that I was describing before is gonna apply here as well. So you'll be happy. You'll be very happy because you're gonna have this gap between covering and non-covering here, and so it's gonna be good. So in the sense that you would get a high gap for when you embed. The issue here is that how to prove that this is a hard problem. So what we made this hypothesis that, and in the paper, I don't have much time, but in the paper, we have more and more details on why this hypothesis may be reasonable. In the paper, we made this hypothesis that this alpha here, which is for the soundness case, how much fraction you will be able to detect that you can cover. We think that alpha could be like as low as 1 minus 1 over e plus epsilon, and t is a constant that is a function of epsilon. And so we believe that this problem is hard to approximate. You know, hard to distinguish for alpha 1 minus 1 over e. And okay, so I can explain a bit more later, but basically here, assuming this hypothesis, it's going to be NP hard to distinguish between, it's going to be NP hard to approximate the k-means and k-median in the L1 metric as high, the gap, the approximation gap is as high as the general metric space. So in fact, if you believe in this hypothesis, and maybe you don't yet, but if you believe in this hypothesis, you will get that the L1 metric for k-means and k-median is as hard as general metric space, which is interesting because for L2, the gap we obtained through this hypothesis is still much lower. And in fact, there is some evidences that L2 should be easier than general metrics. But here, interestingly, we show that L1 is as hard as general metric space. So it's interesting. And so this Johnson coverage hypothesis that we made is nice in the sense that if you prove an alpha value that is smaller than 1 minus 1 over e plus epsilon, you will still get some gap here that is reasonable. You will still get some improved gaps. You get some hardness here. So even if you prove something weaker, you will still get some result. But also, if you prove that that the Johnson coverage hypothesis is false, if you manage to refute the hypothesis, then that means that there is an algorithm that is better than the standard SDP also for this problem. So there is some evidence that it's not going to be that easy to refute. Okay. So as an open problem, the conjecture, this is the conjecture true. Okay. So I think that's the end of the tour. That's the clustering we obtain at the end. I think we have 3 clusters, maybe 4 clusters. So we have the easy land where you have isoperimetric inequality, or you have this nice structure on the metric basically. And then you have the hard, the worrisome land where you have general metrics, and we don't know how to do. And now we learn that L1, high dimensional L1 is maybe not easy. It's maybe as hard as general metrics. There are some evidence that some possibility that L1 is as hard as general metric. That's for example. But then on the other hand, L2 may still be easy. Maybe may still be, and I feel like L2 may admit algorithms that have better approximation guarantees than for L1 high dimension. So I think it's interesting because we learned that from a clustering point of view, the L2 metric is really somewhat easier than the L1. Okay, so let me conclude with a few open problems. So for planar and minor free metrics, I think there are interesting questions, which is like, can you get approximation schemes that are efficient for k-median in planar case, in minor free case? That's still open. Efficient approximation scheme for non-uniform facility location in planar, that's also still open. Like we get n to the poly 1 over epsilon, so that's not very good. And there is also the work we did on non-uniform facility location last year with Marcin and Michał Pilipczuk only works in planar. So for minor free, pitas for non-uniform facility location is still open. So these are like very concrete approximation algorithm questions, approximation scheme questions. For high-dimensional Euclidean space, there is this nice question of whether this conjecture that we've made is true. I think proving either way is a bit challenging, but we will learn both ways. We learn something both ways. So if you refute it, then we learn a new nice algorithm that go beyond the SDP. If you prove it, then we learn that L1 is really hard. So that's pretty cool. And I think the very nice obvious open question here is for facility location in L2 high dimensional. So here it's really nice. I really like this question. It's for general metrics, metric space for facility location, we get a 1.48 approximation, and the hardness is 1.46. So it's very close. Here we are almost happy. The problem is almost solved. For this also will translate, assuming some variant of the Johnson coverage hypothesis. Okay, for L1. Now for L2, the bound we get are much smaller. They are below 1.2 for L2 under any variant of the JCH that is plausible. So there is a beautiful question here that I think would be that, can you show that for high dimensional L2 you can get a better approximation than the general metric case? So from 1.48, can you get 1.45? And then if you can get 1.45, then it means that in fact you have a concrete problem for which L2 is somewhat like a concrete constraint problem for which L2 is easier than the general metric case. High dimensional L2 is easier. And so and I'm suggesting facility location because when it's almost like we are matching, right? So if you could translate the same here, getting the same bounds here in the Euclidean as tight bounds in the Euclidean case, high dimensional, then you will go much below, presumably. So that's one question. And then maybe the last slide is for the 1 median problem when you don't have any candidate centers. So basically, I give you endpoints and a metric that is implicitly given to you, can you find the location of the median, the point that minimizes the sum of the distances? And in L2, it's known as the Fermat-Weber problem. It dates back to Fermat, who asked this question: how fast can you compute it? And of course, if you want to approximate it to 1 plus epsilon, then you can do it very efficiently. If you want the exact complexity of this problem, then it's an open problem. Like what's the complexity class of this problem? And there is also the SLAM variant for the 1 median in edit distance, where you have a set of n strings. You have to find a new string such that you minimize the sum of the distances, edit distances, from the n string to this. So it's very useful for compression. So it's a cool open problem. And I'm going to stop here and thank you for your attention.
Okay, thanks, Vincent, for the excellent talk. Only one clapping in person. Does the audience have any questions? So please type the questions in the chat box, and I can ask Vincent. Okay, so one question from Yossi. So does it seem like the non-uniform facility location is harder than the uniform case?
Right. It does. Yeah, it doesn't seem, except that you can. Yeah, I mean, the fact that you can't treat for example, if you take the linear programming, if you phrase the problem as a linear program, I think all the approaches that are known for like the non-uniform, the uniform case will work in the non-uniform. But really, from the low-dimensional case, we had this isoperimetric inequality. So for actually, I can give slightly more details on that on the example that is given by Arya et al. Here. So it's really like a star, and it's so you can really break this star into pieces using like the isoperimetric inequality. So in the sense that you can say, okay, I'm going to break like these rays here, and the only connection point is point S here. And so the isoperimetric inequality tells you, okay, S is like 1 point, and here you have many points in this ball here. So you have this gap between you have indeed this gap between the boundary size and the inside. Like you have one center on the boundary and say 1 over epsilon inside. So you have really this, you can make a charging argument. You can say, okay, I'm going to mess up on the boundary here, but on inside, I'm going to be optimal. But now in this example, if you increase the cost of the boundary guys, if you mess up on this guy, you are stuck in the sense that whatever you're going to change, like, you can't mess up on this one. And so this makes the complexity, the local search fail, for example, here. And I think that's the issue we have so far. And yeah, and it's and that's the bottleneck for local search. And then going to so for Euclidean, we managed to fix it using the argument I gave you for this badly cut. But for the planar, it's not. Yeah, we didn't manage to make such an argument work. Like it looks like the adversary can play a little bit with how to place these weights, but intuitively, from a complexity point of view, I don't think it's harder. I think the difficulty is just to get the right algorithm.
Okay, so the next question is not a question, but rather a statement. So Adrian Vlado says that for your first question, the geometric median can be computed to high precision and near the linear time.
Right.
This seems related, but I'm not sure if that really answers the question.
Yeah. So that's right. So you can get it to arbitrary precision. But there is this complexity class, which is called this existential theory of the reals, which boils down to solving in a real world complex RAM model. So it's right. So it depends.
Infinite precision, basically.
Sorry. Yeah. Exactly. So that's the and maybe it belongs to there is a possibility that this problem belongs to this class. So there have been some work recently as focused on this existential theory of the reals for like the art gallery problem or other variant of it. And I conjecture that the 1 million also belongs to this class. So I think it would be cool to nail it down. But I agree that for all practical purposes, the complexity of the 1 million is settled. Yeah. Mm-hmm.
Good. So yes. So then the other question is from Robbie Kralgammer. Did you consider direct reductions between different LP norms? That is.
That's a good question. We didn't. No, we didn't look at that. Yeah, that would be interesting. Yeah, that would be. So we consider like reduction between like L1 and edit and stuff like that. So for example, for K-median in edit distance, for example, we could get the same bound than L1. So if I want to add something to this drawing, I could also add edit distance, for example. So there is a little bit of this, but maybe we didn't use the full power of it. So it's a good direction to explore as well, I think.
So yeah, we are running out of time, but let me still state the question. So Anup Bhattacharya asks, is it known whether K-median is APX hard in Euclidean metrics?
Right. Yeah. K-median. K-median is K-median is in Euclidean mixes. You mean L2 as well? Yeah. Well, yeah. It's NP hard for sure. Yeah.
So, and then maybe one more question for me. So you presented in the first part of the talk, you presented results that are parametrized by the dimension and that have a sort of complexity that scales at sort of 1 over epsilon to the d. At the same time, you had these hardness reductions assuming ETH or strong ETH. Do you think there's any chance of establishing this tightness of 1 over epsilon to the d using
right? So exactly. Exactly. So the running time is like 2 to the 1 over epsilon to the d.
Okay.
Yeah, and in fact, so because for example for L2, the APX hardness works in log n dimension, like log n over epsilon squared, thanks to
I see.
Then you can't really hope to get like 2 to the 1 over epsilon to the maybe square root log n or something. I think that's ruled out.
Okay.
But getting the precise constant, I think that's still open. I think people did it for TSP maybe, but for I'm not aware of anything for clustering where you pin down exactly what's the right constants in the exponent using set maybe or something like that, strong ETH or something. That's
all right. Okay, so there's more questions, but we are running out of time. Should move to the next talk. So maybe let's take them to the Slack channel. So please do use the Slack channel. And thanks a lot, Vincent, again.
Yeah, thanks a lot, Megan.